Now we are going to discuss how to obtain Lagrange's equation of motion for a spring pendulum system. Now let us consider a spring pendulum. This is spring, and this is a bob of mass m. So the bob of mass m is attached to one end of the spring. The other end is fixed to this rigid bar. Choose this is the coordinate, origin 0, 0. Now, when the bob of mass m is raised to some height, and if you release, then you can expect two types of oscillations. One is oscillations with respect to the origin. There is an oscillation. Another oscillation is, so this is a spring along this direction. There is a vibration. So there are two types of oscillations. Let L be the equilibrium distance. There is from the origin to this point, the mass m. L is the equilibrium distance, and R the extension from equilibrium. This is the extension from the equilibrium. K is the spring constant. Now, the coordinate of this mass is given as x comma y. Now, this distance is the since this is L plus R, and this angle made by this theta, and this distance is L plus R sin theta, and this distance is L plus R cos theta with the negative sign, because origin is here, and this is a negative direction. So the coordinate x is L plus R sin theta, and the coordinate y is minus L plus R and cos theta. Now let us calculate the kinetic energy of this system. The kinetic energy is half m into the horizontal component of the velocity plus the vertical component of the velocity square. So x dot is the horizontal component of the velocity, so x dot square. Y dot is the vertical component of the velocity, so this is y dot square. So half m into x dot square plus y dot square will be the total kinetic energy of the system. Now let us substitute for x dot. Since x is equal to L plus R into sin theta, x dot is, you have to differentiate with respect to time. This will be R dot into sin theta plus this is L plus R, and you differentiate sin theta, you will get cos theta, and you differentiate theta with respect to t, you will get theta dot. So this is your x dot. Similarly, y is given as minus L plus R into cos theta. You have to differentiate with respect to time, you will get y dot. Y dot is equal to minus R dot cos theta plus L plus R sin theta theta dot. Now let us find x dot square and y dot square. In that expression, if you substitute here, then so once we square this one and square this one, and if you add, you will get this term R dot square, and cos square theta plus sin square theta will be 1. Similarly here also, if you square and add, this is the expression, this is L plus R whole square theta dot square, again into sin square theta plus cos square theta, this will be 1. And the cross terms, this is a positive sign, and here there is a negative sign. So once if you add, this will be 0. So finally the kinetic energy expression is equal to half m into R dot square plus L plus R whole square theta dot square. Now let us calculate the potential energy. So there are potential energy due to two factors. One is because of the vibrational motion, and one is along the because of the oscillation. This is due to a spring. This is potential energy is half k. The k is the spring constant, and here L plus R minus L. So that is your extension. So that is square. So L plus R minus L whole square. So it becomes half k R square. So this potential energy is due to the spring motion. Another potential energy is due to the gravitational potential. mg the height, h is the distance. So this vertical distance is your h. So here m g h is equal to minus L plus R cos theta. Therefore minus mg into L plus R cos theta. So this is the gravitational potential energy. Now if you add these two terms, you will get the total potential energy of the system. So V is equal to V1 plus V2, which is equal to half k r square minus mg into L plus R cos theta. So now let us write down the Lagrangian of the system. Lagrangian is defined by the T minus V. The kinetic energy minus the potential energy is defined as the Lagrangian. So L is equal to T minus V. Now we substitute for T from this expression. Half m into r dot square plus L plus R whole square theta dot square minus V. So you substitute this value here. So this is minus half k r square plus mg into L plus R cos theta. So now this is your Lagrangian of the system. Now let us write down the Lagrange's equation of motion. But this system is having 2 degrees of freedom. The generalized coordinates are r and theta. There are 2 coordinates r and theta. Now let us write down the Lagrangian equation of motion corresponding to each coordinate. So for the first coordinate r, the Lagrangian equation of motion is d by dt of partial dl by dr dot minus partial dl by dr is equal to 0. Then let us find the dl by dr dot. So this you know the expression for L here, and if we differentiate with respect to r dot, we will get m r dot, and if we find d by dt of partial dl by dr dot, you will get, if you differentiate this expression with respect to time, you will get m r double dot. Similarly, let us calculate partial dl by dr. Partial dl by dr, here you know the expression for L, and if you, because you know the expression for L, and here if you differentiate with respect to r, you will get this expression m into L plus R into theta dot square minus k r plus mg cos theta. Now you substitute these 2 values, the part d by dt of dl by dr as well as partial dl by dr in that Lagrange's equation of motion. Then you will get that expression m r double dot minus m into L plus R theta double dot square plus k r minus mg into cos theta is equal to 0. Then let us write down the Lagrange equation of motion for corresponding to the coordinate theta. D by dt of partial dl by d theta dot minus dl by d theta is equal to 0. You take the expression for L and again find the dl by d theta dot. Partially you have to differentiate with respect to d theta dot. You will get m into L plus R square into theta dot. If you find a d by dt of partial dl by d theta dot, so again you differentiate this with respect to time, and first you take this expression m into L plus R whole square, you differentiate theta dot, you will get theta double dot, plus the second time is m theta dot, and you differentiate this term with respect to t, so 2 into L plus R into r dot. Similarly, you have to find a partial dl by d theta. Partial dl by d theta, you know the expression for L. If you differentiate with respect to theta partially, then this expression becomes minus mg into L plus R into sin theta. Now substitute this value in that Lagrange equation of motion. You get m into L plus R whole square theta double dot plus 2m theta dot r dot L plus R plus mg into L plus R sin theta is equal to 0. So you have 2 expressions, equation 1 and 2. The equation 1 is one of the Lagrange's equation of motion, and this is another equation of motion. So there are 2 equations of motion corresponding to these 2 independent coordinates r and theta.